The standard model relies on internal symmetries, written mathematically as U1, SU2, and SU3, dictating how forces interact with matter. But the model treats them as axiomatic inputs. We know they work, but the framework cannot tell us why this specific sequence exists. Modern gauge theory accepts these internal symmetry fibers as given. It essentially appends an abstract internal space to our familiar physical coordinates, without asking where that internal geometry came from. Philip Lillian's Infratier closure framework proposes a structural alternative. Instead of starting with the gauge groups and asking how they act on matter, Lillian's paper attempts to derive the symmetries themselves from a deeper hierarchy of physical constraints. The central thesis treats internal gauge geometry as the compressed relational residue of a deeper operation on physical space. The manuscript carefully partitions its claims. It takes established mathematics, like Lie group theory and Clifford algebra, and completely separates them from the physical hypotheses it proposes, making the logic highly auditable. The goal is to replace a list of empirical coincidences with a specific generative algebra, where each step naturally forces the next. To understand this mechanism, we have to discard the traditional Kaluza-Klein idea of compactification. Dimensional compression in this framework does not mean a spatial axis is physically shaved away or curled up so small we cannot see it. It is defined instead as an informational closure resolution, where independent degrees of freedom lose distinguishability, leaving a restricted observable quotient space. Under stronger closure, the rank nullity theorem dictates observable rank cannot increase. As base dimensions are lost, the unresolved null space must expand. The distinctions removed from the observable quotient do not vanish. They transmute directly into internal relational structure, bound within that newly expanded vertical closure fiber. Lillian calls this exact mechanism independence to relation transmutation. What was once an independent spatial coordinate is now purely an internal gauge relation. As base external disclosure decreases, internal fiber structure expands, creating a vertical space where internal relations can reside. The numerical architecture starts with a distinct physical hypothesis. It proposes an initial, maximally disclosed phase spatial state with an effective disclosure dimension exactly equal to pi. This primitive state admits a specific mathematical decomposition. Pi is partitioned into three, representing ordinary, externally disclosed spatial structure, plus a mathematical remainder. That remainder is the phase residue. It is exactly pi minus 3, yielding a constant of approximately 0.14159. This diagram shows the framework using this exact residue as a single universal compression increment. Subtracting it at each level generates an exact mathematical orbit, stepping from pi to 3 to 6 minus pi to 9 minus 2 pi and 12 minus 3 pi. This entire dimensional hierarchy is generated from that single phase spatial primitive. We never need to independently tune the numerical values for any subsequent tier. This flowchart tracks the mechanism mapping dimension to symmetry. The framework relies on a postulate called minimal relational enrichment. As dimension compresses, newly formed internal relations require a mathematical carrier, using the smallest complex space available. At the first compression to 3 dimensions, the internalized phase structure requires a one-component complex carrier, preserved by a specific stabilizer group. It is an established mathematical fact that the continuous norm-preserving transformations of a one-dimensional complex line form the symmetry group U1. The second compression drops the dimension to 6 minus pi. This chiral closure requires the next available level of complexity, a two-component complex carrier. Preserving both the positive Hermitian form and the complex area form of that two-component space mathematically isolates a single exact stabilizer, the group SU2. The third compression reaches the constraint closure state at 9 minus 2 pi. Following the sequence, this requires an oriented three-component complex carrier. To preserve the complex volume form of a three-component carrier, the only mathematically valid stabilizer is SU3. The framework proposes that these specific complex frames are generated directly by discrete geometric compressions. If we can subtract the constant residue indefinitely, there is an obvious counterargument. Why does the sequence stop here instead of generating an SU4 sector and an SU5 sector? The answer lies in the three-dimensional closure saturation principle. The physics of these closures unfolds on a real three-dimensional carrier space. In established exterior algebra, independent alternating relational grades on a three-dimensional space terminate at grade 3. A 4 form is a mathematical impossibility here. That algebraic limit directly maps to the fourth numerical iterate in the orbit, 12 minus 3 pi. Because there is literally no new independent closure grade available on a three-dimensional carrier, this iterate marks the absolute onset of closure exhaustion. The finite structure of the standard model forces is not an arbitrary limit. It is hard-capped by the algebraic limits of three-dimensional space itself. This chart visualizes the strict coherence invariant equation that governs the entire model. D plus C plus R equals pi. The total phase spatial coherence budget remains constant across every compression. During the first 3 ordinary closures, only 2 variables are active. D represents external space, the visible disclosure. C represents the stored closure residue, the geometry locked inside the gauge fibers. The anomaly arrives at the exhaustion coordinate, n equals 4. Here, the internal closure capacity bound is breached. The final compression quantum does not vanish. Denied an independent closure grade, it overflows into a new channel, defined as the recoherence residue, R. Three-dimensional Clifford algebra provides a mathematical route for what happens next. At maximum spatial closure, the three-dimensional pseudoscalar squares to -1. This suggests an algebraic mechanism where maximal closure triggers a phase-like reentry, allowing coherence to reappear. The underlying dimensionality is strictly conserved. It is relentlessly repartitioned among external space, internal gauge fibers, and recoherence boundaries. Elegant geometric correspondences do not automatically constitute a finished physical theory. To cross that threshold, a model requires strict paths to physical falsifiability. First, future physics must derive the constant additive compression rule dynamically from microscopic mechanisms. Postulating a repeated subtraction of pi minus 3 is structurally efficient, but it must be proven. Second, extracting the SU3 group is insufficient on its own. The specific constraint assigned to that 3-component carrier must mathematically dictate actual dynamical confinement behavior observed in quarks. Third, the mathematics demand a measurable qualitative spectral transition or stability shift directly at the 12 minus 3 pi exhaustion threshold. If experiments cross that boundary with no observable anomaly, the model fails. Until falsified, the Infratier framework remains a testable proposal that gauge geometry is the stabilized shadow of compressed spatial information.